Welcome to Talk 11 of Human Factors in Design. I'm Giacomin, and today I'll be discussing the design of controls. Controls being the way we get our information or we make our requests to some sort of a machine or a service or a software or a system of some sort. So there's a relationship between a person and something that's being designed. There's an interface, and somehow I have to make requests. So I have to somehow input or control the device. So today we're going to talk about the series of human factors, ergonomics considerations about what happens with controls and what kinds of principles or techniques a person can use to think about them and to design them efficiently. So where does this question of controls start? Where does it come from? As I've mentioned several times, there was a big acceleration in ergonomics and human factors in the mid-20th century. There was a period when aircraft tended to look, their cockpit, a little bit like what's going on in this photograph. This has got two positions, one for the pilot, one for the co-pilot, two sets of controls, lots of indicators, lots of displays, lots of toggle switches. There's a lot going on. As a matter of fact, people who work in the area of ergonomics and human factors began to refer to this period in the history of aircraft design particularly as the era of the knobs and the dials. Lots and lots and lots of simple control actions. Set something, set a valve, set a pump, change the position of something. Lots of simple mechanical or electrical switches to operate, to the point that there may be many hundreds present in the environment. So what kinds of controls or control devices were available at the time? Well, the things we're familiar with from everyday life. Push buttons, foot buttons, simple toggle switches, complicated ones, rotary switches, knobs, dials, wheels, levers, handles, pedals, the whole ensemble of simple mechanical things which we can usually use our hand or our foot to move and to push or turn into some position indicating something we want the machine to do. A little bit after the period, we began to see different input devices. More recently, we've come to rely a lot more on things like the computer mouse, the trackball, the digitizing tablet, the light pen. So there's a whole range of simple things. They all have in common the fact that they tend to be physical, they tend to be mechanical or electrical, and we tend to use a hand or a foot to indicate something we want by moving, twisting, changing a position of something. What kind of simple design rules emerged? There's many. In the next few slides, I'm just going to list a couple of key ones, some of the big ones that everyone's always thinking about. In reality, there's books and resources dedicated to this, and there's a wide range of considerations you can look up and deploy. But some of the important make or break type considerations. One of them is the assignment of the control action to either the human hand or the human foot. We've already discussed this previously in the talk about posture, and we've outlined in detail in that talk why large forces but slow and not so accurate motions tend to be assigned to the leg and foot, whereas faster, more rapid motions, typically of a more sensitive or selective nature, tend to be assigned to the hand. Other simple control design considerations from ergonomics and human factors: the size of the control device or the control interface should usually be proportional to the stereotype. For example, if I'm driving a car I would find it somewhat surprising, though it's certainly possible, and it doesn't necessarily not work accurately, but most people would find it surprising if we were turning a steering wheel which was small enough to use just with our fingers, rather than a rather large wheel that we use the complete hand, if not both hands, to turn. So sizing the thing somehow proportionally in some sort of a logical relationship to what might be the size of the thing that's being actuated at the other end of the control action, that makes a lot of sense. It helps simplify the mental model, and it makes the thought process a lot simpler. Another very related, very similar consideration, the forces and torques that the interface requires from the person to make the decision and input the control action should be kept relatively low. They should be kept within the range of what's doable and comfortable for the person. So stereotypes, try to go with what the person is thinking. Control forces or torques when you're turning something one way or the other, try to keep them, again, proportional to what the person usually applies as a force or torque when they're doing similar things. Another control selection consideration, controls are always designed with some amount of consideration to the stereotypes that may be adopted in that particular context, in that particular culture, with those particular people. So, for example, here is a simple display of the type that you see on some old-fashioned radios, where there's an adjuster knob and there's some sort of a pointer which moves across a scale. If it's a radio, that would be the frequency scale that you're changing the channel selection. This kind of a device, in theory, there's no reason why a designer couldn't make the little wheel go clockwise or counterclockwise. Or there's no reason why, regardless of the wheels turning, we couldn't assign the pointer to move left to right with the wheel, or instead the other way, right to left with the wheel. So there is freedom to design, but the designer will stop and think from the point of view of the mental model, from the point of view of the metaphors and all the things we know about this, from the point of view of the typical situation a person faces in this context, what would be the expectation? And almost always a designer will design the system such that the input wheel turns in a clockwise manner. Since the medieval period, most, if not all, clocks in this world have had hands which turn in a clockwise direction. That is a very natural expectation when we see something turning or rotating around a point, because the world is full of clocks all around us. Why would we do the opposite? Would that not possibly lead to some mistakes on occasion? So respecting stereotypes of a physical, cultural, or other nature is an important consideration in control design. Then a very, very important issue with controls is what's referred to as the control response ratio, or CR ratio. It's illustrated again with something that looks like a little bit like an old-fashioned radio. We have a tuning dial, a tuning knob which we can turn, and we have a pointer moving across a scale, again probably as a radio with the frequency indication on the scale. And the question becomes, what gear selection, or if you prefer electronically, what gain should the designer assign to the relationship between how much I turn and how much the needle moves? I can design it in many different ways. I can design the gears or the electronic gain of the system such that, as you're seeing on the left of the image, you have a small turn of the wheel, does a really big movement, across the frequency spectrum of the linear pointer. Or, as a designer, I could choose for the opposite. I could make it such that maybe it takes a full turn of the wheel just to make a little movement of the pointer across the linear scale. So this relationship between what I'm doing, which is the turning, and what the machine is doing, in this case moving a pointer across a scale, that relationship is up to the designer to choose. So the question then becomes, I wonder what might be a good value of the gain or a good value of the relationship to choose. And the nature of this relationship is what's illustrated here in this diagram. A control response ratio that's rather low, which means that if I turn it a little bit, I move very quickly the needle. That's good at getting roughly to the neighborhood where I want to be, near the frequency I want to be. But given that there's a big jump for every degree I turn, it's rather hard, going a bit back and forth, to get it to zoom in to exactly precisely the frequency, or let's say the point on the scale that I want. If I move quick, it's a bit rough and crude, and when I'm in the right neighborhood, I have real trouble adjusting the fine adjustment or the fine tuning to get it exactly at 53.00 megahertz for the radio station. Instead, the opposite, which is where the control ratio, the control response ratio is rather high or large, in that case, it's the other way around. Yes, if I'm in the right neighborhood, if I happen to be near where I want to go, I can get it adjusted quite precisely and right on the 00 of the frequency very quickly. But if I started from far away, I have to keep turning to get to the neighborhood of where my frequency is. So there's a trade-off, like everything in design. There's a compromise to be made between a high gain and a low gain, between a low CR ratio and a high CR ratio, where one is better at one thing and the other is better at the other thing. What ends up being chosen by most designers in most applications most of the time is some sort of a compromise in the middle. And you can see in the diagram there's the crossover point between the adjusting time, how long it takes to adjust the fine tuning, and the travel time, which is how long it takes to get into the right neighborhood. There's a point where the two cross over, sort of in the middle, sort of a compromise, not too bad at either. That, when you only have one gain setting or one set of gears between the knob and the dial, that's the sort of value a designer goes for. And there are specifications and tables and handbooks to go see what that value might be in given cases. Now, what other considerations do we have? So stereotypes need to be considered. Torques and sizes and forces need to be considered. The relationship between what I'm doing and what the machine is doing as a gain needs to be considered. There's a few other things that need to be considered. One of the next ones is, what about the way the interface feels? What kind of feedback resistance is the interface going to provide? When I push it, is it going to be hard to push or easy to push? Is it going to just fall over or resist me when I'm moving? Because this affects how I interact with the input control, and this may affect the precision of the things I'm telling the machine to do. So a designer needs to give some consideration to the different natures of resistance that the steering wheel, the joystick, the laptop keyboard button, the mouse, the trackball. You have to ask some questions about what should be the feeling in terms of the stiffness and resistance of this thing. Are there different types, and do they achieve different things? Are the different types better at different things, or are they all the same? And basically there's different types and they get used in different circumstances. The first type, as shown on the list, is elastic resistance. The the second is friction, the third is viscous, the fourth is inertial. Let's talk about them in a little detail. Feedback resistance of the type referred to as elastic. Elastic means a spring, an elastic band, a rubber band, something that when I pull it with a force, it deflects by an amount X. Or alternatively, if I push it and compress it, let's say, an amount X, it resists me with a force proportional to that value of X. So a linear spring of the type found in a pen that you click on to open it, a linear spring of the type that might be in the keyboard of your laptop, for example, those are examples of elastic resistances. Elastic controls are present in most interfaces. Give it a try. Look around the house tonight. Check your laptop, push the button, click the button on the mouse, do something on the television. Most interfaces, certainly most traditional ones with buttons and knobs, will have an elastic spring of some sort, of some amount of stiffness in it, because A, the more I push it, the harder it gets. There's a nice linear relationship between how far I push and how hard it's pushing back on me. So it's easy to understand, and it's telling me something about how far I've pushed it. I can feel it tactile through my fingers or my toes. The linear spring is also incredibly important in safety critical applications. For example, trains or underground carriages, such as on the London Underground. The control stick has what's referred to as a dead man control, a dead man spring on the joystick. The idea being, it has happened many times over the years that a driver of a train might get ill, might even have a heart attack or something very severe, and keel over, and there's no one controlling the train. Now, if the controller, the speed controller, the joystick that you push forward to make the train go forward, if that just sat there where the guy left it, this would be incredibly dangerous and you would crash into the buffers or into something at some point. So a dead man spring, as the name suggests, is a quite stiff spring that's in the joystick. I push it forward to make the train go forward. If I get ill and I fall off the control and I let it go, the spring guarantees it pops back to the zero position, which means it'll start stopping with no forward traction. It'll start to slow to a halt, which is the safe thing to do. So for many, many, many safety critical systems, regardless of what else the designer does, an elastic spring of some amount of stiffness must be in the interface control to guarantee that if you let it go and you're not actually controlling, you're not driving, you're not monitoring the machine will bring itself to a halt. A second form of resistance, which is not too distant from the first one, is the static or Coulomb resistance. Static or Coulomb resistance is the kind of friction you get when two materials are rubbing against each other and you want to move one respect to the other and they're not moving, and boom, then the friction is broken and it starts to move. Coulomb or static friction is not a linear spring that you push a little and you get a little force back, you push harder, further, and you get more force back. This is really, you push until some limit of the friction needed to break the two surfaces is reached, and then you start to move and there isn't much friction after that. The static or Coulomb friction is used in all of those controls, all those buttons and knobs and sliders, where it's really important to hold the fixed position. If I'm doing some work in a mastering or mixing studio with music and I'm adjusting the gains or the filters on my deck and I push to a certain position, I don't want that when I release my finger from the control that any little movement, any little shaking of the desk or any little shaking of the mixing or mastering board changes the setting. So we need some friction, some static in the device such that when I get it to a position, it stays locked there until a fairly big force is furnished by my finger to move it some more one way or the other way. But when I leave it, a little bit of wind or a little bit of motion or vibration of the environment will not change that setting. So static or Coulomb friction is quite often, quite intentionally, built into all kinds of controls, buttons, knobs, steering wheels, and so forth. And and the amount of it is usually chosen based on the specific application. A third type of resistance, which is rather common in many controls, is the one referred to as viscous damping. Those of you of an engineering persuasion, if you have some background in engineering, you may have studied dynamics, you may have studied vibrations or acoustics, you may have heard someone talking about viscous dashpot, a damper or a shock absorber of an automobile. These are all devices, typically with hydraulic fluid or oil of some sort in them, and they're devices where two ends of the thing move. There's usually some sort of a piston or channel. Some oil is made to flow when one pushes with respect to the other, and the motion of the fluid across these channels slows things down. It smoothens things out. It provides what's referred to as damping or viscous. Think of a viscous fluid, something thick like jelly. Viscous damping. When you run jelly, something thick, it slows you down a bit. So viscous damping and specific units, mechanical devices which have orifices and tubes and pistons and things to achieve that, is a very common component of many systems. So viscous damping is quite often built into the base of a joystick, or viscous damping is quite often provided in the steering system of a car by a little damper which is attached down inside the car onto the steering column, so that when it rotates there's a little bit of damping keeping it from vibrating too much. So viscous damping, it's not too important to think about the engineering aspects of it, but from a design perspective and a human factors ergonomics perspective, what's important here is to realize viscous damping is something that slows down, smoothens out, reduces the vibration, reduces the bouncing about, and makes the control action smoother. So maybe my hand's shaky, and maybe on the joystick the input I would be giving wouldn't be that smooth, it wouldn't be that clear for the machine. But thanks to the fact that at the base of the joystick there's something that's a bit sticky and a bit viscous, and some sort of a device which is not letting me move easily, it's resisting the motion of the joystick, the vibration can get smoothened out a bit, such that my motion, my request to the machine of what it should do, such as an aircraft, turn right, turn left, and so forth, that request would be smoother, simpler, and more interpretable by the machine, because some of the jitters and some of the high frequency motions will have been filtered out and removed thanks to the fact that these sticky devices at the interface have smoothened out the motion of the control surface. And finally, a somewhat related concept is also what's referred to as inertial resistance. Some interfaces, for example on airplanes, traditional airplanes from 40-50 years ago, would have had rather high inertial resistances, and there were occasions where that was very helpful. What's a high inertial resistance? For example, an airplane from 40-50 years ago, and you've seen these in the movies, the plane has a problem, the plane is going down, and you see the pilot and the co-pilot grabbing the stick, and both of them pulling as hard as they can back on the stick with all their upper body strength, trying really desperately to get the tail airfoil or the wing ailerons back enough to try to pull out of the dive. Now, there is some dramatic effect in the Hollywood movies. However, there is some truth to that scene where the plane is crashing and the gentleman is pulling with all his might back onto the stick, because the joystick or the wheel was controlling the very big piece of the tail or the very big piece of the wing, the one that moves. It was controlling it through wires run on pulleys all the way from up here where the joystick is, all the way 20, 30, 50 meters back to where there was the tail of the aircraft, and the tail probably weighed many hundreds of kilograms, and it's going in an air wind motion that might be 100 or more miles an hour. So this was an example of inertial resistance. I tried to move it. I'm moving it through cables or gears or whatever, and the thing I'm moving is really, really big. And something really big and heavy doesn't want to move. That's a form of resistance. It's a mass or inertia resistance. So many traditional machines where there was a lot of manual input to control different parts of the machine, those particular control surfaces and those particular control actions on the part of the operator would have been exhibiting what's referred to as inertial resistance. It really doesn't want to move, and in many cases that's a good idea. You don't want an airplane to suddenly, just because you bumped into the stick or you dropped a coffee on it, you don't want the airfoil to move up 10 degrees and pitch the nose down or the nose up of the aircraft. So inertial resistance had many safety implications, some of them quite useful in certain circumstances. So sometimes in an aircraft or a complex system such as a road vehicle or a train or something else, a degree of inertial resistance may be built into the electronic control system even today, despite the fact there are no pulleys, no cables, and it's not mechanical anymore. So there may be a little bit of programming and a little bit of components in there to provide a degree of inertial resistance where, of course, in the fully electronic servo-assisted system, that isn't anymore a natural part of the system. It's not necessary, but it is built in many cases because there are situations where it's helpful from a safety perspective. So designers have at least 4 types of resistance that can go into an interface. Actually, most interfaces will probably have a combination of 2, maybe even 3 of these operating, maybe one of which was fully designed and thought through, and the others which are natural results of the shape and function of a button or a wheel or knob. Physical systems particularly tend to provide some of these resistances automatically just by their physical nature. It just happens. So even if the designer is not calculating, determining things in great detail, a certain amount of some of these resistances will be occurring nonetheless. Now, designers can count on lots of help and lots of support for the design of simple controls for simple interfaces. There's lots of guidance, various standards, there's handbooks, there's ergonomic and human factors texts. We could show many examples. We'll just show a couple just to give the idea, a flavor of what's out there. For example, a hand wheel on some sort of a machine. Hand wheels, there's plenty of design guides where recommended radii or diameters of the wheel, the size of the wheel are specified for different applications. Recommended thicknesses of the wheel, such as the rim diameter D here, are recommended. The resistance that the wheel should sort of resist you and not want so easily to turn, those might be specified. All kinds of informations will be specified for specific machines and specific applications. Buttons, there's all kinds of standards, design guides and recommendations in relation to buttons because there's so many used in everyday life. It's not just the keyboard or the computer, there's buttons everywhere in the world and they're all of different sizes and shapes. So what size should it be to fit a finger? How stiff should the spring be inside to resist my pushing down? If I use the palm of the hand rather than the finger, does this have any effect? Does that change anything about the sizing? how far apart should two buttons be on a keyboard, etc., etc. Lots of recommendations. Now, it's important to note, because this is incredibly important, that when you, as a designer, face a situation where there need to be a lot of controls and or displays in the thing you're designing, and with a cell phone or computer we might be talking about a lot of menus. With some sort of a machine such as a vehicle, an earth mover, an aircraft, a helicopter, submarine, we might be talking about control panels with physical controls rather than just touch controls as on the cell phone. But either way, when we're facing the challenge of designing a system where we know we can't avoid, it can only be simplified to a certain point, and beyond that there's still a lot of things that the person needs to choose from and specify and request as an operator of that piece of equipment, we've got to be careful, because what naturally occurs, unavoidably occurs, is mistakes or errors. For example, these images, the drawing at the top and the pictures down at the bottom, these are images of the Apollo spacecraft from the late 1960s. You can imagine the difficulty for the 2 or the 3 astronauts possibly flying all the way to the moon when they're operating this. There's hundreds, literally hundreds of toggle switches, rotary dials with multiple settings, A, B, C, D. What are all these controls? Some are valves, some are battery modes, some are oxygen pressure regulations, some have something to do with the firing of the retro rockets. All the mechanical and electrical systems at that time, in a somewhat pre-computer era, all of the things that needed to be chosen and selected and changed at some point for some reason needed to be done manually. They had to be manual operations. So with hundreds of controls to deal with, the question then becomes, what can we do to minimize these errors? One thing that was done, and it seems incredible today, is that there was an operator manuals. It's not something you see much in the movies, but the pilots on the Apollo had a big stack of books, this long, and if Houston said, we need you to change your pitch angle, or we need you to adjust something on the temperature or something else, they would say, go to page 155 of the operating manual and follow the sequence that's stated and typed in the text of page 155. And you'd go there and it'd say, go to switch 210 and flip it off. Go to rotary dial 55 and turn it to position B. Go to the set of toggles from 25 to 35, flip them all into the middle position. This is the way things were done before we had computers to automate, simplify, and do all the setting of the multiple systems based on a single input from the operator. So in that era, simplifying things was incredibly important. And even today, despite the fact we have computers and automation which can remove a lot of the backroom choosing and moving and selecting from our consciousness, we'll let the computer set 300 valves for us once we've said what we want. Despite the fact that we have computers to simplify, even today, the things the machines can do are many more. So, okay, we're not seeing all the chaos in the back room, and we're not dealing with every little mechanical pump and valve and thing that's in the machine. However, the machine does a lot more things, so we're back to the problem of lots of things to select from. It's still a complicated interface. So, what kinds of things do people do as human factors ergonomics experts to address this issue? At the time, a lot of work and a lot of research was done, and slowly over the years some consensus emerged about good practice, what's good design practice, and control coding became the term to express a set of rules or a set of guidelines of good practice. And what types of things were the control coding for these kinds of simple interface structures? Well, there's several. The first, location coding. Group together all those controls, whether they be toggle switches, rotary, whatever. It doesn't matter what the control surface looks like in practice, but group together all of the ones that do something similar from the user's point of view. You know, if I want to turn on the heater controls in my car, everything related to the heater box and the heater system and the air conditioning as well is all grouped on the center console in one place, and usually through a very small set of dials and knobs and buttons to make the selection choices. So group together things which logically in your mind might be grouped together. So design the interface panel based on how the person's thinking. Shape coding. Why not give a shape to the button, the dial, or the icon that you see on the screen of your cell phone? Why not give a shape which is very clearly imitating or at least related to the shape of the thing you're thinking about, the one you want to actuate? What about size? Size is another coding process. Wouldn't it make sense, wouldn't it seem logical to most people that something that has a big effect or is really important might be a bigger button or a bigger control wheel, and something that you don't use very often, maybe it's not such a big adjustment, maybe it's a fairly minor thing? Wouldn't that be the kind of thing you'd give less prominence and less pride of place on a dashboard or a control panel by assigning it to a smaller button? Seems logical. Important, big, not so important, small. That's something I think most people would automatically, intuitively assume. Mode of operation coding. Why not make the interface control operate in a similar manner to the thing it's controlling? Is it really a coincidence that all the cars in the parking lot turn on the windshield wiper with a control stalk with something that's attached to the steering wheel, and it looks a lot like a windshield wiper, and you sweep it up to click it on, which is exactly the direction of motion of the windshield wiper. So you use something that reminds you of the thing you're controlling, and it gets operated and actuated in the same manner as if you were grabbing with your hand the windshield wiper on the screen and pushing it to the right to make it actuate. Seems like a great simplification, makes a lot of sense. The thing works in a way, that's the metaphor. I'll make the control surface based on the same metaphor. Labeling coding. Many times you might do your location, your shape, your size, you might do all the best you can, and there's still a lot going on, and it's still somewhat confusing. So you say, just to make sure about things and to give the person an extra chance to avoid mistakes, I will stick labels on it, such as the ISO codes. If you look inside, for example, again, an automobile in the parking lot, all the little warning lights, all the control switches, everything has a little symbol. It's not arbitrary. The symbol used by BMW is the same one used by Fiat, which is the same one used by Aston Martin. They are internationally standardized ISO standard symbols. They've been agreed by committees such that all around the world we use the same ones, which should hopefully help people to avoid becoming confused when they face something and they're not sure of it and they're looking for guidance at the symbol. And then finally, color coding, again an intuitive one. I think most of you will have experiences with things that are color coded. Red, almost universally, is used as a color for those control buttons, those control interface components which are safety critical. Red is a color that's exciting, it's energetic, it's subjectively stimulating. We tend to use red or orange for those things which you'd probably want to be actuating when there's a stimulating, exciting, maybe scary situation underway. Green usually indicates a normal operating function. Yellow and white usually intermediate to normal functions. We tend to see panels either in a machine or on the screen on a software or an app. We tend to see menus and panels with fairly simple standardized use of colors which everyone can recognize. Now, in terms of examples, location coding. The drawing that's at the middle here, which you can see there's a steering wheel, there's a piece of dashboard on one side of the steering wheel, a piece of dashboard on the other side where the center console is, there's a bit of dashboard underneath the bottom near the knees and legs. This is a simple geometric representation of what was a test facility, a test buck, as the name is used in the industry, by car companies. So you might have a cabin layout for your vehicle. It might not be the real one, might just be pieces of wood or simple mock-ups, but you lay out things in the positions you're hoping to use, and you might bring people in to check their reachability, whether they can reach things or not, check their opinions on things, check that they can actuate everything carefully. Now, this particular diagram and the data that's in there is not too important to fine detail, but what it's an example of is studies, which they did quite a few in the 1970s and 1980s, about where people expected to find things. For example, as is written at the top here, front windshield wiper controller. Where does a person expect to find a control in a car for turning on and off the windshield wipers? And if you look here at the different zones, zone 1, zone 2, 3, 6, zone 9 and 10 being stalks, just on one side or the other of the steering column next to the steering wheel, what you see is that the vast majority of the people, 30% to the left, 28% to the right, zones 9 and 10 in the diagram. Most of the people were expecting to find the windshield wiper controller on a stalk next to the steering wheel. Probably these tests were done in Europe, because at the time that's where most manufacturers in most countries, in some countries it would have been on the right hand side of the wheel. In some countries the manufacturer favored the left hand side, but most European vehicles of the time would have had the windshield wiper stock. So there's a mental model or a stereotype or a metaphor or a preconception, if you prefer the term, that when I want to turn it on, I guess it's going to be there. Instead, we can see a certain number of people were expecting it in other places. Now, for example, in the diagram, zones 4 and 6 at the bottom seem a bit unusual by European standards. Very rarely did European cars ever put the windshield wiper there. But 4 and 6, down at the bottom of the dashboard, were not at all unusual in North America at the middle of the 20th century, 1950s, 1960s. Lots of American large automobiles would have had the windshield wiper controller in either zone 4 or zone 6. So this is an example of location coding, bringing together things of the same type and then asking the question, where's the most stereotypical location where the people want it? So, I bring together all the heater controls. Should I put it in the center console, or does it go somewhere else? These are the kinds of design questions we have. Just grouping them is the first step. And then there's also the associated question, which is addressed here, which is, I wonder where's the best place to put it, even when I group them. Shape coding. It was not unusual at the middle of the last century for aircraft controls, various safety critical ones in particular, to have handles where there was either a label or a picture on it, or the handle itself had a shape which recalled or brought to mind the actual thing that was being controlled. So here we have a series of suggestions that were made in academic studies 20, 30 years ago. These are shapes, some of which were actually close to the ones that were used in practice. you can see what looks like a turbine or a turbocharger blade at the top left. That would have been the recommendation for the control that actuates the turbocharger on a piston-driven engine. When you get above a certain height and the oxygen becomes rare, you can actually turn on the turbocharger. Others, such as on the right, that semicircular shape, might be recalling slightly the flaps. Others might be reminiscent of the landing gear or the wheels. So the idea was, maybe we could help the pilot, maybe if we're lucky we could avoid a few mistakes if we make the control surfaces, the handles and the buttons, shaped like the thing that you're controlling, the actual thing at the end of the chain which is being controlled, or perhaps if it's not possible to completely shape it, at least draw the picture of it on the handle or the button to help the person to identify it. Size coding, most remote controls these days are relatively carefully designed. Most remote controls, you will notice as soon as you pick it up that some buttons that you need to use all the time and that are really important to you, and that if you make a mistake it will really irritate you, those buttons tend to be quite large. And those buttons which you probably don't use that often, they tend to get smaller and smaller. And in the 1990s, Sony had a very nice remote control where one side of the remote control had only very small number of really important buttons and they were really big. But if you wanted to program things, adjust the image and do lots of, if you enjoyed tech and you wanted to play with it a bit, you could flip it around on the other side, and on the other side there were lots and lots of little buttons to adjust different settings and so forth. So using the size of the buttons to ensure the most frequently used or the most important ones are obviously visibly larger, maybe even stiffer than the other ones, that is a fairly standard practice. Mode of operation, we've already referred to it in the previous example. The windshield wiper stalk on any kind of a vehicle is an excellent example of something where the control interface is clearly reproducing the artifact that's being controlled in shape, in size, in motion, in logic, in metaphor, in everything, sometimes even almost in the speed of actuation. And label coding, we said ISO standard symbols are in use all over the world. There was a time that you would buy an aircraft or a car or a boat or something, maybe a television, and you would see the labels on the buttons written in natural spoken language, written in Italian, English, French, Spanish, Chinese, Russian, whatever. But over the years, most manufacturers and most businesses have adopted international standards because it's going to make it a lot easier to sell or export products to different markets if the first line of reasoning is some sort of a symbol which hopefully everyone can learn, and thus regardless of the language they speak every day in their home, they can hopefully spot this and identify and not make a mistake in using that part of the control interface. And color coding is all around us. It's in the menus of your software on your laptop, it's in your cell phone, it's in the buildings of the university, it's everywhere to be found. It doesn't need much explanation. Now, design classics from the point of view of controls, I'm designing to make it as easy as possible, as logical as possible, and to minimize the errors and the workload associated with telling the machine what to do, getting the idea in there so it does what I want. If we look at design classics about that specific consideration, one of the most elegant ones you can find is the Honeywell T87 thermostat, various versions of which are still in production today. You still find them in new build homes today. They're all over the world. The T87 is an old system. It goes back to the 1950s. What is elegant and what is clever about this from a human factors ergonomics point of view is that the interface is designed considering several human characteristics so as to make the interface easier to use, more pleasant to use, and to make mistakes or errors less likely. For example, the control here is rotary. It's rotary because turning your wrist, grabbing something with your fingers and turning your wrist around that axis is an incredibly natural, very straightforward, and actually rather comfortable motion to make. You know, if we're doing this for 6 hours, yes, our wrist will get sore. But it's one of the more comfortable motions, it's one of the more comfortable uses of the hand, it's one of the easiest ways to interface with some sort of physical machine and give it a control input. So this device is rotary. You grab the outer shell and you turn it with your fingers, and the spring is not particularly stiff, and it's rather smooth and damp, so it's nice and smooth, got a good feel to it. Other things from a human perspective, if you look where the needles are in the middle, you see that there's a temperature scale at the top, and I presume that's in Fahrenheit in the units used in North America. We have numbers going from looks like 80, 70, 60, 50, from about 40 or 50 to 80 something, which is the comfort range that you'd expect in a person's home. And then you have the same numbers from about 40, 50 to 80, 90, exactly the same at the bottom. Now the two needles, one of them is the temperature scale, measuring the temperature in the room. The other one is the setting. So not only is the motion, not only is the interface of the controller nice and comfortable and natural and obvious and intuitive, but so is the reading of the data. There's a scale and another scale. They're identical. They're both rotary. The needles are the same. One of them is what's going on in the room, which will be obvious to you. When you look there, you'll know right away which needle is the temperature of the thermometer. And the other one is the setting or the target you're giving to your boiler and your radiators to bring up the temperature in the house. That's the temperature, at least for the moment, you would like. So this is a very natural, very well thought through system. The diameter is roughly the size of a 50 percentile man or woman of that age, of that period of time, the 1950s. People have gotten bigger since then, but in the 1950s that would have been the hand size of a 50 percentile. The motion is comfortable, the motion's natural. Both pieces of information, the room, which is the reality, and the target you'd like, they have to match up and they have to become aligned. They're both there in the center. You can see if they start to align or not. It's a very clever controller. Simple, elegant, but clever. And more recently, another very clever, very simple, very well designed controller. 1980s, 1990s, the emergence of PlayStation and the PlayStation controller introduced this specific one, 1994. The PlayStation controller is still with us today. Many apps and many games are still emulating or copying the layout of square, triangle, X, and circle. The idea here was we can group on one side of the controller the intuitive, natural concepts of moving something up, down, left, or right, and by laying it out on a cross, that's as simple and natural to human beings. It goes back in history, thousands of years. We've been doing drawings, maps, and other things, laying out the motions in that manner. We've got a couple of system settings in the middle, the ones we don't use very often. So we've got one thumb free to control one logical idea, which is the positioning. We've got something in the middle, we won't be using that often, maybe just the beginning or end of the game. And on the right, we've got another thumb free to concentrate on selecting between 4 different options which a given game is offering. So the idea of separating position on one side, operating motions or modes on the other, and secondary, infrequently used things in the middle, all of it fit to the size of a 50th percentile hand of the period, such that you can use both hands comfortably and hold on to it for long periods of time. Absolutely elegant, absolutely clever design, respects lots of human factors, ergonomics considerations, particularly of the cognitive type. Divide the activities the game can perform into 4 categories. Use the 4 symbols. Once the person's learned that, they can migrate from game to game as long as the number of modes or activities are fitting this breakdown of 4 at a time. They can use the same controller for multiple games with multiple purposes and multiple settings. So very clever design from a cognitive point of view, from a mental model point of view, and from a control coding point of view. Well, that's the end of today's talk. Thank you very much for your time and your patience. Again, I hope that there were some items of information which will prove useful to you. And thank you again, and speak with you again next week.